Okay, in this video, let's recap some of the concepts from energy so far, and then see how we can apply the DEWNC to solving some problems. So we know that if a system is closed, the total amount of energy in that system will be conserved. It'll convert from one type to another, but the total energy in a closed system is conserved. When you have forces then outside of that system doing work, then you're going to change the amount of energy. So we want to see what's the difference between these conservative forces doing work and non-conservative forces doing work. So we've talked about work in general, and if we take all the forces, conservative or non-conservative, doing work on an object or a system, we'll see that that'll cause a change in kinetic energy of the object or system, and that's where our EWOC comes from. Now, if the system only has conservative forces, such as a spring force in a spring system or gravitational force in a gravitational system, then this mechanical energy that's associated with U spring, UG, and kinetic energy will stay conserved, and this is where we came up with the EQ goose. Now, what happens when we have more forces besides just conservative forces like spring and gravitational? Those forces are potentially doing work on the system, and what happens then is my total mechanical energy changes. No longer is delta E equal to 0 when non-conservative forces do work. And let's just remind ourselves what some of these are. So the conservative forces are the forces associated with potential energies, which are gravity and spring force. But non-conservative forces are forces that are associated with changes in other types of energy. So for example, friction or drag, those are forces associated primarily with changing the thermal energy or increasing the temperature of an object, as friction causes an increase in the vibrations of those molecular forces of an object, causing its temperature to increase, but not associated with stored energy. And the same thing can go for like an applied force. An applied force can be used to change the kinetic energy of an object, but it's not associated with storing any force like a conservative force of gravity or spring. So we're going to deal with these these non-conservative forces. And so let's look at a couple examples for how this could work. In the first example, let's take a 10-kilogram block sliding across a desk with a velocity of 5 meters per second. There's a 14 Newton force of friction between the desk and the block. We want to find the amount of work done by that friction. Now, if I know the force, I could first of all figure out the displacement and then find the work by applying displacement times the force of friction. But let's do this using DEWNC. So in DEWNC, all we need to know is my initial velocity of the box is 5 meters per second, and my final velocity is 0. So my final kinetic energy is 0. So as the box slides over this displacement, we know force of friction is acting in the opposite direction, doing negative work, causing that delta K to change. And if there are no other forces, then we can say, well, the change in mechanical energy is the change in kinetic energy, which is equal to the work done by non-conservative forces, which is the work done by friction. So there's no spring potential changing, there's no gravitational potential changing, it's all delta K. So in this case, K final minus K initial is equal to the work done by friction. This is 0, this is minus 1/2 times 10 kilograms, so that's minus 5 times 5 meters per second squared, which will be minus 125 joules. So it's a quick way of finding the work done by non-conservative forces on a system where the mechanical energy is changing. Now, mind you, I can use this, and if I wanted to find the displacement, I could use the fact that the work done by friction is going to be the force of friction times delta x times the cosine of the angle in between, and this is 180, so this is a -1. And so we could use this information then to go find delta x if we wanted to. Sorry, it's coming off the page a little. But it's not necessary. This is a quick way of finding the work done by the non-conservative force of friction.